Welcome back. In this next Minitab tutorial, we're going to talk about the tools that we use when we have the case of an ANOVA problem. In addition to that, we'll talk about the case of testing for equal variances. So if we have two or more groups and we want to run for a test for equal variances, we'll walk through that tool. And then we'll use the tool to do the analysis of variance to test for the means. After that, we will talk about the case of applying power and sample size planning to our ANOVA problem, but recognizing that the power and sample size planning applies to any statistical tool. And although there's some different data entry points we have to understand, the same approach, the same thought processes are consistent across various different types of tests. Again, our main focus of this module is if we want to compare two or more groups. We begin by testing for equal variances. If we assume normality of the groups, then we will use a Bartlett test, or if we do not make this assumption, we'll use a Levene test. After that, we'll talk about the testing of means using one-way ANOVA. I'm going to do it two different ways. I'm going to use the actual ANOVA tool itself within the stat menu of Minitab, and then I will follow that up by using the assistant. I generally like to cover the tools outside of the assistant first because we get a sense of what some of the levers or some of the things we have to check. And if we go right to the assistant, there's certain assumptions that are made for us. It's useful sometimes to get a little understanding what those assumptions are. After that, we're going to go through power and sample size planning as it would apply to ANOVA, but also the generic concepts would apply to any test. In order to compare two or more groups, we can use the stat ANOVA as the main menu, and we'll do that first, or we can use the assistant. And here's just a picture of the assistant, and over the assistant you can see we have a test of means, and then we have a test of standard deviations or variances with standard deviation squared would be our other option there. So both of these things we're doing are in multiple places. They're either under the regular ANOVA tool menu or they're under the assistant. To test for equal variances, we have to make this big assumption or this assumption about the normality, and we have results based on whatever we pick for that assumption. Now I'm going to jump over to Minitab at this point. I've given you an Excel file, and inside that Excel file I've given you data which is on fees, and we have different lenders. In this particular example, we actually want higher fees. Higher fees are making greater profits. So we're looking to see if there are differences between the lenders, and there are 5 different lenders, and so we want to be able to use test for equal variances and ANOVA to compare the different lenders. We're going to begin by going over to stat ANOVA, and then we have our one-way ANOVA, and if we scroll down here we have an option for our test for equal variances. And let's go ahead and click that first. And you'll notice that it gives a couple of menus. Either we have things in stacked or unstacked format. In this case, all of our response data is in one column. We put the commission fee there, and then we can click on the lender code. If we click on the options command, you'll see where it says confidence level. This is our alpha value used to create our confidence intervals. And then we're going to begin by checking the box that says use test based on normal distribution. I'll run this as well without that box checked, but let's begin by checking that box first. We're going to go ahead and hit OK. Under graphs, there are some different summary plots they make. You can make a box plot. You have some different options there. We'll let the default one stay for now. I'm going to go ahead and hit OK, and Minitab is going to come back and give me some results. And if I scroll over to the session window first, again, we can see the null hypothesis. All the variances are equal versus at least one is different. It's telling us the Bartlett method is based on the normal distribution. And then if I scroll down, I get a p-value. I will also notice that on my chart itself, because I had the normality assumption, Minitab is giving me the Bartlett test there. It's also giving what are known as Bonferroni confidence intervals. And anytime I can draw a line through all of them, that's another way to test for equal variances. So I can look at the line or I can look at the p-value. In this particular case, they both come back and say there is no difference in the variances. In ANOVA terms, this goes by the phrase the homogeneity of variance or equal variance assumption or constant variance assumption. Regardless of the group, there's no evidence to suggest that any of the groups have more variance. Now, it does look like lender 4 has perhaps more if we had additional data or a different one, but based on the data that we have collected here, no evidence to suggest that. Now, if you'll notice, this next time I'm going to run the same tool. So I use a little button up top here to bring that same tool back up. And when I did that, this time under Options, I'm not going to check the box that says Use Normal Distribution. I'm going to hit OK and hit OK. And Minitab is going to come back. It's going to give me different intervals because it's going to use a different method. And over here, it's going to give me some what are called non-parametric tests. In this case, the p-value is 0.204, and once again, there is no difference in the variances. I can still draw a straight line. Obviously, my line isn't so perfect, but I could draw a straight line if I had drawing skills through all of my data set. Would be another way of showing that there is no evidence to suggest that the variances are different. Once again, confirming the homogeneity of variance assumption. Next up, I'm going to go ahead and compute or compare the means. This time, I'm going to use a one-way ANOVA test. And once again, I have options about whether the data is stacked or unstacked. In this case, I have all the data, all the y variables stacked in the response, and the lender code is the factor. When I click on Options, one of those options is to assume equal variances. We can use that or we can uncheck that box. In this case, we're going to check that box to assume equal variances. Now, we can decide this assumption based on historical knowledge or opinion of the process. We could be influenced a little bit by the fact that we already did a test of equal variances and we had no evidence to suggest they were not equal. So we can use this information to make a decision about what assumption we think is appropriate. These are assumptions, and if we change the assumption, we'll get slightly different p-values. Now, a lot of times, even though we get slightly different p-values, we don't get different conclusions. So the p-value might change a little bit, but unless it changes a lot, our conclusions will be consistent. Go ahead and hit OK there. This time under graphs, again, we have some different data plots. The one that we like to click on is the 4-in-1 plot. This 4-in-1 is our 4-in-1 residual plots. This is also looking at our ANOVA assumptions. And in fact, we can also use this one to test for our homogeneity of variance. I'll show you that here in a second when I run the tool. That's an HOV on the chart up there on the screen. So we'll use the 4-in-1 plot. And this same tool is also there in the regression tool and other tools where we have residuals as one of our options. We go ahead and hit OK and hit OK. And when we are all done, Minitab is going to come back and give us a couple of outputs. When I look at this output, I will start by looking at the residual plots. I'm going to draw a line down the middle. On this side of the residual plots, I am looking at the normality. This is after fit. So residual is based on after we fit the data based on what group you're in. And so now we are accounting for the groups. And because of that, we can see that even though maybe our overall distribution is not normal, our residuals are normal. Our residuals appear normal, which is another way of saying that the groups appear normal, either looking at that chart or looking at relatively close fit to the probability plot. As I discussed before, if this graph were to look like this, like a big horseshoe, that would be an indication of not fitting normal. But if those points are relatively close to that line and that graph looks bell-shaped, that's a pretty good reasonable assumption of normality of the groups or the residuals. Also, if we look at this chart over here, this is another indication of our constant variance or homogeneity of variance. And again, for each of the levels, and you'll notice there's 5 of them, so each group we get some fitting, and then this would be the scatter about that line, and we get similar results. If I had a group that was like this and another group that was like that, then I might argue about whether or not I have a homogeneity of variance assumption. In this case, I do not have that. I have reasonable spread of my residuals, pardon me, for that. If my data is in a data collection order, I can also look to see if I have any trends over time. No clear trends here. No clear, wrote the word clear on the board up there, trends. So my assumptions appear to be okay. Now I'm going to look at the means, and if I look at the interval plot, I might notice that there appear to be a gap between lender 1 and lender 4. There may be additional between lender 4 and some others, but there's clearly a gap between 1 and 4. If I scroll up into my session window, Minitab tells me that I ran a test to see if all means were equal versus at least one is different. It is said I assume equal variances. I had 5 levels, and I have a p-value here of 0.003, suggesting that I have a significant mean difference. Now, in this particular case, my R squared is not real high. My R squared here is only at 20%. Ideally, I like R squared to be 50% or higher, but even though it's at 20%, there is still some significant differences going on here between, for example, lender 1 and 4. I get my confidence interval, and the last thing that the software gives me is the pooled standard deviation. This is my sort of averaging or pooling, or weighted averaging, I should say, of the standard deviations from each of the group into a single estimate. Because we have no evidence to suggest the variances are different, the software pools all these together into a pooled standard deviation term. And that is our main usage of the ANOVA. One thing I will also show in the ANOVA, there's also the tool analysis of means. And in the analysis of means case, I could put in my commission fee versus my lender code. And I could hit my button, and this would be one that showed me that lender 4 appears different than the overall groupings of them. By the way, if I want to look at the data without lender 4, I would go to Data Subset, and I could put in under the column lender code, and it says include rows that match, or I could do exclude rows, and I could get rid of number 4. If I did that, then I would have a data set with just 1, 2, 3, and 5. I'm not going to do that, but you can do that on your own if you want. The last thing I want to do was to use the assistant. For ANOVA, the assistant is a hypothesis test. I run that. It gives me my options over here. I can do the standard deviation test, or I can do one-way ANOVA. In this case, I have all of my data in one column and my lender code. It's giving me some choices for alpha that are typical. And it even gives me some options to help with power calculations, saying what is a practically significant shift. In this case, we'll just leave it blank for now. And we'll go ahead and hit OK, and the software comes back. And when it comes back, it gives us this output. And under the comments, it says you can conclude that there are differences at the 0.05 level. In looking at the chart, it appears that group 4 differs from group 1. So they're telling you which ones differ from each other. And you're getting an indication of the overall p-value. The software puts things in an order. Over here is the smallest. Here is the largest. It's turning these red because there is this, sorry about that, there is this lack of an overlap there, suggesting that 1 differs from 4. Now, if the goal is to get the most fees, then lender 4 we see to getting a better business or better profitability with, and moving forward, we would consider maybe trying to get more business at lender 4 or try to understand why some of the other ones are not doing as well. Again, lender 4 wasn't really shown to be bigger than, say, 3 and 5, bigger than 1. So there may be some additional thinking that may go involved in a final recommendation. So as we often do, the data is giving us direction, but we often have to make decisions about what to do with that information. The last thing I want to do in this tutorial is, if I jump back into my slide again, we went through these various tests, and the next section we're going to talk about power and sample size planning. They're all under the power and sample size menu. We can do this for different tests we've done in class. These are all in the options over there. And we're going to begin with this example shown right here, where we're given some information about the process, and we're trying to figure out what is the power to detect a shift of 600 for this situation. Let's go ahead and hit come back to Minitab, and this time we're going to go to Stat, Power and Sample Size, and looking at our options, one of them is a one-way ANOVA. And I begin by putting in the number of levels. If we have 5 lenders we're interested in comparing, and the sample size, we start out by saying we have 10. The value of difference that we're looking for is 600. The power is what we're trying to figure out, and the standard deviation is 500. Under options, it's going to ask us for the significance level, and we're going to put in 0.05. For some of the tests, it'll even ask you for the direction. Do you want it to be greater than or less than? That's when we only have 2 groups. We don't do that when we have 5 groups, because we'd have too many odd combinations, if you will. So when we have 2 groups, we can also look at direction. For now, we're just going to put in equal versus unequal. We hit OK, and this time we're going to go over here and run. The software automatically gives what's called a power curve. This lets us see our power as it relates to our maximum difference for a given sample size. If I scroll up to the session window, you will notice that the alpha, again, 0.05, S is equal to 500. I've got 5 levels. If I have 5 levels, I really need big N equal 50. And when I do that, I get a power value of 0.5. So the power is 0.505, or round to 0.51, whatever, around 50%. In other words, if the shift is 600, if the true shift is 600, there's really only a 50% chance I'm going to detect that, given the number of samples I've taken and the other criteria I have selected in terms of standard deviation, etc. Now, if you're thinking that's too low, which often it is, a lot of times I would like my power to be roughly in the 0.9 or 90% range. I mean, yeah, we'd like it to be 95, but that usually means more samples. So a lot of times we're satisfied if we can get in the 0.9 range for power, or 0.1 for beta error. And let's go ahead and think about how we can do that. Well, one thing we can do is we can increase power by increasing sample size. So let's come back to our same example. This time, though, instead of telling you the sample size, I'm going to tell the software the power, and I'm going to leave the sample size blank. I'm not going to change the other parameters. And when I hit OK, I get this same curve back, but this time it's for a sample size of 23. And I notice here now that my target power was 0.9, but the power for the n equals 23 for a difference of 600. The power is now 0.909, and I have a much better chance of detecting a shift of 600 given the other parameters of the problem. So just trying to show you how things can change a little bit with the sample size. I'm going to do that one more time, but this time under the graphs, I'm going to add some additional numbers. So instead of giving you the 10, let's do 10, 30, and 50. And this time when I do it, the software will still solve for its recommended, but it'll also give me curves for other ones. And then I can start to say, well, if I wanted to not detect the difference of 600, but maybe a difference of 400, what type of sample size would I need? So just another way of kind of exploring some what-if analysis. All right, the last thing I want to do with power and sample size is we're going to come back to this. I'm going to come back to my original case, though. And let's say I had 10 was all I really could afford, or I really was being pressured to do this in 10 per group, because again, that's 50 total. And I say, how else can I do that? Well, another way to increase my power is I can play with my alpha term. If I make the alpha a bigger number, so make alpha 0.1 as opposed to 0.05, that can increase my power. Or I could reduce the standard deviation. Maybe I run a more controlled study. I take more similar types of loans such that the standard deviation is closer or lower. And if I have this condition, and I go ahead and I run this, and I look at my chart up there, I can see that when this went from 500 down to 300, my power went from 505 to 0.94. So I increased my power to 0.94 by using a more controlled condition. What I'm trying to show you here is one thing we do in statistics or experimental design is we will control the noise variables to get less standard deviation to help us see mean differences with fewer samples. This is a theme we'll come back to later in the class. All right, well that was it for showing you how to use test for equal variances, the one-way ANOVA, and power and sample size planning, recognizing that we go through a very similar thought process if it was a t-test or a two-proportion test. The recommended sample size, of course, is going to change, and proportion tests are going to take a lot more samples, but we can explore those things similar to what I did in today's module. Thank you, and good luck with your next assignment.